Thank you for joining us today. On today's Engineers Newsletter Live program, we'll be discussing electrification of HVAC systems, often referred to as decarbonizing. Many customers and municipalities throughout the United States and the world are taking action to reduce their carbon emissions. One of the tactics they're using that affects the HVAC industry is the reduction or removal of natural gas for heating. This means our industry will face the challenge of heating our buildings with reduced amounts or no fossil fuel. This E&L will cover the motivation to electrify, areas currently affected by this trend, and the potential products and systems to meet electrification needs. To walk us through the discussion, we have Dan Gentry from our Applied Product Support team and Charlie Jellin from our Applications Engineering team. Charlie's going to start us off.
I'm going to cover 3 sections to start the program. First, we'll provide some background on the topic of decarb and electrification. Next, we'll discuss heat pump design considerations, and then talk about some potential product solutions. We're going to start with some basic definitions, starting with the terms that we hear most often when we talk about this topic. First is decarb, which is short for decarbonize or decarbonization. Decarb is the process of reducing or eliminating carbon emissions. And there are many ways to reduce carbon emissions in HVAC systems. One avenue that is being pursued is electrification, which is a second term. It means using electricity in place of burning fossil fuels in your building. An example would be heating your building with an electric heat pump instead of a gas-fired boiler. Now, electrification by itself will not help reduce total environmental emissions. So why are we going after it? Why are we trying to electrify our buildings? The answer is renewables. The hope is that renewable energy sources power the majority of the electric grid in the future. So all electric buildings and utility grids powered by renewables is one path for a sustainable future. But before we talk about the future, we need to address some of the concerns of today. And one question we get asked a lot is, why is burning fossil fuels at the power plant better than burning fossil fuels in my building? To help answer that, we put together a little example. We're going to compare the carbon emission totals for a couple different building and grid scenarios. First, we'll look at a 100,000 square foot commercial office building that uses both gas and electric energy sources to heat, cool, and power the building. We picked a building in the upper Midwest that uses the RFCW E-Grid subregion. This area covers multiple states, including large sections of Illinois, Ohio, and West Virginia. To come up with an energy consumption total for this example, we used the U.S. Energy Information Administration Commercial Buildings Energy Consumption Survey results, commonly referred to as CBECS for good reason. It shows that commercial office space consumes about 80 kBTUs per square foot. So for our 100,000 square foot office building, that means we'll consume about 8 billion BTUs of energy. Also from CBECS data, we can get an idea of the split between natural gas and electricity usage. Since the building is located in a heating climate, we assumed a slightly higher than average usage of natural gas at 30%. But before we calculate the carbon emission for this building, we need to understand the difference between site emissions and source emissions. Site emissions will be the emissions from burning fossil fuels at the building itself, typically to heat the building, heat potable water, or for cooking. Source emissions are emissions associated with burning fossil fuels at the power plant to generate electricity. Source emissions will be different across the country based on the mix of generating sources, which are predominantly coal, natural gas, nuclear power, and renewables. Okay, back to our example. We can calculate the site carbon emissions by converting 2.4 billion BTUs of natural gas into carbon emission equivalents, which equates to 140 tons of carbon. Now, the other 70% of this building's energy was provided by the electric utility, the source. For the RFCW subregion, the mix of energy sources that power the grid are shown here. 33.5% of this grid's energy was provided by carbon-free sources, such as hydro, wind, nuclear, and solar. 44% was from burning coal, and the last 22% was from burning natural gas. The eGrid average carbon emission rate for this region is 1,166 pounds of CO2 per megawatt hour of production. And this does include 4.8% of average grid loss on the system. So using the data, the source carbon emission calculation comes out to 957 tons of CO2. This calculation is based on the average emissions for the utility grid and does not account for marginal or non-baseload emission rates. All right, here's the summary of what we've covered so far. At the bottom of the table, you can see we added both site and source carbon emissions to get a total of 1,097 tons of carbon emissions. We're going to consider this our baseline for an average building in operation today. Next, let's look at the impact to carbon emissions if we switch the building to utilize all electric power. For heating, let's assume we switched from burning natural gas on site to using electric heat pumps. It's obviously a lot more complicated than that, and we'll get into some possible product solutions in a little bit. But for now, we'll assume we figured out how to electrify the building. We'll also assume these heat pumps are on average 3 times more efficient than gas-fired heating equipment. This value is going to change based on your climate. Warmer climates will provide higher heating COPs, while colder climates will yield lower heating COPs. So the total electricity consumption, for our example, will increase because we're heating and cooling with electricity. But the total power consumption went down because we're using more efficient technology. The site carbon emissions are eliminated because we're no longer burning fossil fuels on site. We'll assume the same utility generation mix as the previous example. So calculating the source carbon emissions, we get 1,094 tons of CO2. That means our total emissions went down slightly from the previous example. The common question we get at this point is, why didn't the emissions drop much further? Well, the makeup of the fuel that powers this specific utility grid is less efficient than burning on site. But if you move this building to a different grid, you'd get different results. Like I said at the beginning, electrification by itself is not going to lower total carbon emissions. We also need the grid to be powered by more renewables. So let's look at that example. We'll fast forward to 2030 and go back to our original gas-electric building. We'll assume the energy draw from the building is exactly the same. But the mix of energy supply for the power plant has changed. We'll assume the amount of carbon-free sources has doubled from 33.5% to 67%. Coal's contribution has dropped to 10%, and natural gas is about the same at 23%. The site carbon emissions will be unchanged from the original alternative. This was just to keep the example simple. It's possible that by 2030, gas-fired equipment will be more efficient and therefore have a lower emission rate. On the source side, and with the new energy mix, the source emission is calculated to be 404 tons of CO2. So that's a 63% reduction in source CO2 from the previous example, and a 50% reduction in total carbon emissions down to 544 tons of CO2. For the next alternative, we'll look at an all-electric building on our example grid in 2030. Again, the site carbon emissions drop to 0 because we're not burning any fossil fuels on site. The source emissions are calculated at 462 tons of CO2. So this provides a total carbon emission reduction of 58% from the first alternative. Now, one thing to note, In our example, we assumed that this specific grid was able to double the amount of carbon-free energy in the next 10 years. And that might seem like a lofty goal. However, there are a lot of utilities that are striving to exceed that mark. Xcel Energy is pushing for 80% renewable energy by 2030. Con Ed said they'll achieve 100% clean energy by 2040, and SG&E is already at 85% renewable energy. All right, so let's run our example building with 85% carbon-free sources. To go with that 85%, we'll assume a 5% coal contribution and a 10% natural gas contribution. Using this mix and calculating the total emissions, you can see they go all the way down to 213 tons. That's an 81% total emission reduction from the baseline. So hopefully this helps answer the question of why are we electrifying our buildings? The main reason is the thought that the grid will become heavily powered by renewables. And if you're burning fossil fuels on site, you won't be able to take full advantage of that renewable power.